Hi, everybody. Hope everyone had a nice Thanksgiving. Okay. Let's give people a few seconds to log on. Okay. All right, looks like we're hitting a critical mass. Okay, so let's continue. So one is surprisingly, we only have 3 classes left, including today. I thought for some reason we had class on next Thursday as well, but Wednesday is the last day of classes. Um, so one unfortunate bit of news is that I'll be giving the final assignment out soon, either this evening or tomorrow morning, at some point, depending on how much I get done before my toddler comes home and then after he goes to bed, and before I go to bed. Final assignment, by final assignment I mean exam, right? So this I it's formally called a final assignment, I think. It's an assignment due the last day of class. I have to use that terminology, I think. So it's going to be like a homework assignment, except it's going to be on like whatever material I'd like to ask questions about. So the whole class is open game, and it'll be like I think I'll give you it'll be supposed to be around a 3 hour. I'm going to design to take you like at most 3 hours, but you can spend. I think I'll give you like 6 days or something to do it. So you can do it whenever you like over those 6 days, and take as long as you want to do it. So that's the plan. And I'll let you use your books and your notes and stuff like that, but ask you to do it, to in contrast to the homework, to do this one by yourself. So 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 it'll be a bit different from a homework assignment in that sense, in that you'll have to do it by yourself, or I'll ask you to do it by yourself, but you'll still be able to use the book or the notes, to do it. And I'll so so it might be a little bit different than if in-class final exam, whereas an in-class final exam, I might ask you questions that were, say, identical to something we've done in class or a homework problem or something like that, where because it would be a timed exam, I'd want you to not have to like reinvent the wheel, and just maybe like show me something that you know or learned, rather than something more like these might be more like homework problems, where there is some aspect of it that you have to figure out, because since you can use your book and things like that as a resource, the book notes and stuff like that as a resource. So it'll be somewhere in between what a typical homework assignment feels like and an exam feels like. So typical exam in a proof-based class. Okay. So I'll of course send out an email and stuff when I with instructions and things like this, but the format will be somewhat similar to a homework. You'll upload a version of it to Canvas, just like you uploaded the homeworks, but this time I'll grade it rather than the grader. Okay. So let's get back. So any questions about that? Sorry. Sorry. there's anybody have any questions now, we can also chat about it on Thursday after you have it in your hand, things like that, and I'm of course open via email as usual. Okay, so if there are not any questions now, we'll revisit it again on Thursday. Okay, so last time we started discussing the Fourier transform. So the Fourier transform.
Can you share your screen?
Sorry. I can't wait till I don't have to think about these things. Maybe next year, next fall or something. Okay. So the Fourier transform. So the definition we saw last time. So definition. So given f in L1 of Rd, define f hat of xi to be equal to the integral over Rd of f of x times e to the minus 2 pi I x dotted with xi dx, where here x dot xi is the dot product. Let's see, inner product on Rd. Plus xd. xd where x is the vector x1 through xd. xi is the vector in Rd as well. xi1 through xd. D, which means that f, and last time we showed that this is in fact bounded and continuous, a bounded and continuous mapping. So this is less than or equal to the L1 norm of f. And the mapping f hat is continuous on L1 of Rd. Or rather, what I should say is f hat. Let's just write like this: f hat is continuous, and f hat is a continuous function on Rd. Given an L1 function, the Fourier transform spits out a continuous function. Okay, and so last time we proved these two properties. This was done last time. And the theorem we stated at the end of the last class was the inversion theorem, or the inversion formula. So theorem Fourier inversion. So if f, so given an L1 function, you can define its Fourier transform. So if I have f in L1, and if f hat happens to be an L1 function, then I can recover f of x from f hat. Then f of x is equal to integral over Rd of f hat of xi e to the 2 pi I x dot xi dxi. So this is the analog. This Fourier inversion theorem is the analog of the theorem we proved about Fourier series in the beginning of class, namely that if you have a function, a 2 pi periodic function, with Fourier coefficients that are absolutely summable, That's the analog of the assumption that f hat is an L1. So if you have absolutely summable Fourier coefficients, then the Fourier series converges, and you can reconstruct the function as a as a limit of the partial Fourier sums. So the reconstruction formula for Fourier series is the discrete analog of this reconstruction formula for Fourier inversion. So if I know that if I have an L1 function and f hat is an L1, I have an alternative way of writing my function f. It's given by this formula, and it turns out this is quite a useful formula. Um, Especially in the context, just like for Fourier series, especially in the context of PDEs, which we'll see in a minute in the next couple of classes, for solving PDEs with constant coefficients, in fact. Okay, so so we're going to prove the Fourier inversion theorem, this version of it. But before we do, we're gonna work up to a bit, and we're gonna understand several properties of the. It's not a super easy proof. So we're gonna work up to it by understanding the Fourier transform a bit, and we'll get into quite a detailed study before we prove the inversion theorem. So I'm not sure if we'll get to the inversion theorem today in class, but we'll get to it certainly next time. So some properties. So let's prove coming soon. Let's start with some properties of the Fourier transform. Okay, so let's let f as we have a be an L1. Let's let tau be a vector in Rd. Oh dear, I've used both n and d for the dimension in my notes. Let's see if I can correct this. And let's let A be a linear transformation from Rd to Rd. Linear transformation. Then one, so a lot of these are going to follow directly from like properties of the Lebesgue integral. So I'll leave these all as exercises, in fact. So one, if I define f tau of x to be equal to translation, so I'm going to taking f and translating by tau in the argument. So this is f of x minus tau. So if I take the function and shift it to the right, or shift it by tau, then translate by tau, then f hat, there's a nice formula for f hat of tau. F hat tau of xi is just equal to e to the minus 2 pi I times f hat of xi. So translation in space corresponds to, so I'll use some language throughout. So I'll say, I'll refer to the x variable as the physical side, or the space side, and I'll refer to the xi variable as the Fourier side, the Fourier variable. So translation in the space variable in x corresponds to multiplication by a factor like this on the Fourier side, right? So rotation on the Fourier side. Two, if I let e tau of x be the function e to the 2 pi I x dot tau, then e tau applied to f hat of xi. So I take so not applied. So if I multiply f by this phase, then this is equal to f hat of x of c minus tau, sorry. So these, this is the dual version of the property 1. Okay, property 3. If I let a minus t be inverse transpose of A, so I take the matrix A, so A is a linear transformation represented by a matrix. I take its inverse transpose. Then F precomposed with A hat of C is equal to the 1 over the determinant of A times F hat composed with A inverse transpose of C. Okay, so this is how Fourier transform behaves under general linear transformation, invertible linear transformation. Last, if I let f twiddle of x be f of, so it's special case, f of minus x, then f twiddle hat is equal to f hat twiddle. So twiddle means put a do a reflection. Okay, and then I want to highlight a special case of 3. So if A is an orthogonal matrix, so A transpose equals 1, and the determinant of A is equal to plus or minus 1, then F composed with A hat is equal to F hat composed with A. In particular, if F is radially symmetric, if A is a radially symmetric function, then so is F hat. Radially symmetric means that if I write F of X and I use notation, I write F is F of R times e to the I in polar coordinates. This is given by some function g of just absolute x. There's a function g of one of a positive number such that this equals function g of absolute x. So if f is radially symmetric, then so is f hat. That's nice. If A is a dilation, so A x is equal to lambda times x, where lambda is bigger than 0, for every x. Then, so A is lambda times the identity. Then f, if I let f lambda of x is equal to f of x over lambda, then f lambda hat of c is equal to lambda to the d times f hat of lambda times c. So this is how Fourier transform behaves with respect to rescaling a function. Okay, so all these formulas come in handy and follow directly from the definition of the Fourier transform. So these are elementary properties of the Fourier transform, and they can go give you exercises given that you've already encountered such things, such um, the actions of symmetries on the Lebesgue integral of a function. Okay, so just like for Fourier series, so let's move on to more refined properties. So just like for Fourier, so general principle, analogously to Fourier series. If f is localized in space, implies that f hat should be smooth. And vice versa. F smooth implies f hat localized. So smoothness of the function is going to imply localization of its Fourier transform, and analogously, if the function is localized, then the Fourier transform is going to be smooth. So how do we see? And there are many different ways of seeing this or making this precise. Is there a question?
What do you mean by f being localized?
Let me. Okay, so let me state something specific, and then I'll describe to you what I mean by localized. Localized. What I mean by localized is, say, think of something as an example to keep in mind. Keep a function that's compactly supported.
Mm.
So it doesn't have. It's not like something with. So well localized in space means like I can find a ball that contains most of the support. Most of the mass of the function.
Okay.
So so that's what I mean by localized. But I'll try and make it precise in a second exactly what I mean. But yeah, just as a heuristic, localized means localized support. Okay, so let's let so notation. And for the moment, it'll be compactly supported functions. So let's let B. I always change my notation for the ball radius R. BR X is the ball of radius R centered at X. So it's all Y and RD such that X minus Y is an absolute value less than R. So it's the ball of radius R centered at X. And we have the following proposition. So let's let f be an L1 function. And support of f is compact. So I contained in a compact set. Then, couple of things. Then, on the one hand, f hat is C infinity. And so this is a manifestation of localized function means smoothness of the Fourier transform. So if the function is compactly supported, then f hat C infinity, and moreover, formula A, d alpha of f hat is equal to minus 2 pi I x to the alpha f hat. So if I put the hat over here on the side, I mean the hat of this whole thing, rather than drawing a big hat, I'll put the hat on the side. And moreover, if support of f is in the ball of radius r are around 0, so if the support vector contains a ball of radius r, then b d alpha f hat L infinity. I can't remember if I've been using L infinity or just sub infinity. Is this the for the notation here? But okay, if the L infinity norm of the alpha of f hat is less than or equal to 2 pi r to the alpha times f and L1. Okay, so I've used some funny notation in this statement of this theorem. Let me explain the notation. I'm using what's called multi-index notation. So notation, so we can understand the statement. This is called multi-index notation. Just a basic compact way of writing mixed, lots of mixed partial derivatives. So multi-index notation, if alpha is a vector in RD with components in N that are natural numbers. So alpha is equal to alpha 1 to alpha d, alpha j are natural numbers. So just take vectors with natural numbers as their components. Then d alpha is given by d by dx1 to the alpha 1, d by dx d to the alpha d. Oh, what do I write? D alpha. So it's alpha 1 derivatives in the x direction, alpha 2 derivatives in the alpha derivatives, alpha 1 derivatives in the x1 direction, alpha 2 derivatives in the x2 direction, etc. And it's used in this context in the setting where we can swap the order of partial derivatives. So nice. We always use this notation when they're applied to nice functions. And x to the alpha, if I raise a vector to the alpha power, this means the product from j equals 1 to d of xj alpha j to the alpha j. And absolute alpha equals the length of alpha of the multi-index, which is just the sum of the alpha j's. And okay, there's a partial order on multi-indices. So we can get fancy. There's a partial order. Alpha is less than or equal to beta. If alpha j is less than or equal to beta j, for every j, alpha is less than beta. If alpha is less than or equal to beta, and alpha equal to beta. Okay, so this is multi-index notation, and so what I mean here by d alpha of f is just its absolute alpha number of partial derivatives in various different directions applied to f hat. And then you see I get r raised to the length of alpha here. Okay, so let's prove this proposition. Proof of the proposition. One is that first note that property A implies property B, or the conclusion A implies conclusion B. To see this, since, well, d alpha f hat of C, in property B, I want to measure the absolute value. I want to measure the L infinity norm, so I want to take the sup of all the absolute values over all C in RD. So I'll examine this quantity for each c. What's this equal to? This is equal to just by formula by a, this is equal to minus 2 pi I x to the alpha times f hat c, which is equal to what? This is equal to absolute integral over rd of e to the minus 2 pi I x dot c. It's just the Fourier transform of this object, minus 2 pi I x to the alpha f of x dx, which is less than or equal to 2 pi times, I'm just putting absolute values brutally inside the integral. What do I have? I got x to the alpha times absolute f of x dx. And then since the support of f, since f is supported in the ball of radius r under this hypothesis, then most this can be is sorry, this should be x to the absolute alpha. The most this could be is r to the alpha. So I just brutally bound this by r to the alpha. So this is less than or equal to some constant times r to the alpha times the L1 norm of f, which is what we asked for in property B. Okay.
Just a
yes.
Small interruption. 2 pi should be 2 pi to the power of alpha. That doesn't really matter.
Yes, yes, thank you. 2 pi to the alpha. Thanks. I didn't add it. I had it correct in my notes. And let me emphasize here, just in this integral as well, that this is integral over only the ball of radius. The support of f is contained in the ball of radius r around 0. So this integral is only the ball of radius r, and that's why we can pull out r to the alpha. Okay. So for A, so now we want to prove part A, which is this formula, which is to take a function, take its Fourier transform, and then differentiate it. Differentiation amounts to multiplication times 2 pi I x, and then taking Fourier transform of that. So let's prove part A. Proof of A. Let me sync the file real quick. Proof of A. It suffices to show for alpha equals 1, right? Because then we can just induct. Since if it holds for, length of alpha is equal to 1, for alpha is equal to 1, then 2 pi I x times f also has complex support. And we can induct. And then let's just prove it for d equals 1 for simplicity. So proof for dimension equals 1 for simplicity. All of the extra dimensions do in many of these cases just confuse us. Okay, so we want to take the derivative of f hat of c, right? So we take a look at the difference quotient. Fix a c, and let's examine this difference quotient. What's this equal to? Well, this is integral of e to the I claim it's equal to this formula. So e to the minus 2 pi I h times x minus 1 divided by h times e to the minus 2 pi I x dot c f of x dx. And all I did here was just factor out this. Let me rewrite this, as it looks terrible. this is equal to integral over r e to the minus 2 pi I h times x minus 1 divided by h times e to the minus 2 pi I x dot c f of x dx. And then we remark as absolute h goes to 0, the quantity e to the minus 2 pi I h dot x minus 1 divided by h tends to minus 2 pi I x, pointwise, and x, right? Because this is just, this is the derivative at x equals 0. This limit, right? This limit is a derivative at 0 of the function, of the exponential function. Okay, so moreover, so what do we want to do? What we want to do is just apply dominated convergence, right? We want to take the limit as h goes to 0, this integral. In order to do that, we need to pass h through the integral, which means we need to apply dominated convergence, and we'll do that by via applying the dominated convergence theorem. So moreover, this quantity e to the minus 2 pi I x h dot h times x minus 1 over h is less than or equal to 2 pi times x for every h. And therefore, the integrand is the whole thing, right? E to the minus 2 pi I h dot x minus 1 is less than or equal times e to the minus 2 pi I x dot c times f of x. This is just less than or equal to 2 pi absolute x times absolute f of x, which is bounded, which is less than or equal to, since x is, so what I'm trying to say is, since x is compactly supported, this is an integrable function, right? Integrable since f is integrable and compactly supported. So by dominated convergence, theorem, f hat of c plus h minus f hat of c divided by h tends to integral of minus 2 pi I x times e to the minus 2 pi I x c f of x dx, which is just as h goes to 0. And this latter thing is just equal to the thing we want. This is equal to the thing we wanted, as desired. Okay, so this completes the proof, and the remark is that we have the formula for the derivative. So the derivative of the Fourier transform. So in 1D, f hat prime of c is just equal to minus, you pre-multiply by e to minus 2 pi I x times f, take Fourier transform of that, see. So this formula holds as long as, so, okay, so we used the compact support of f in the proof, but what we really needed was for this function to be integrable, right? So the formula that we just proved holds as long as this function is integrable. So i.e. as long as f decays fast enough for the integral of this object to converge. As long as f, as long as this happens. Decays fast enough to apply the dominant convergence theorem. Yeah, so this is for one derivative. And then if we want more derivatives, then we need f to decay faster, right? So this is the decay of the Fourier transform, or localization properties of the Fourier transform lead to smoothness. So not only is f hat differentiable, we have this formula, and then we can keep differentiating. So f hat as long as f hat is, so if you keep iterating this formula, you see that if f hat is in Cn, if x to the n times f is in L1. So the decay of f leads directly to the smoothness of f hat. Okay, so now let's cover the kind of the opposite direction. So the smoothness of f hat leading to localization properties of the Fourier transform. So now let's do f smooth leads to f hat localized, or rather decaying. Okay, so proposition. This one's a little bit trickier. So let's let f be Cn function, and assume that d k f is in L1. Sorry. D alpha of f is L1 for every alpha less than or equal to n. So for every multi alpha less than or equal to n. Then if I take alpha derivatives of f and then take Fourier transform of this, this is equal to 2 pi I xc the alpha times f hat of xc. This is a nice formula we have for derivatives of f. We had an analogous formula for in the case of Fourier series, if you remember. This becomes extremely useful when studying PDEs. So this formula, analogous to the one for Fourier series, because it turns derivatives by taking Fourier transform. You can turn derivatives of a function into multiplication by xc. So that's quite nice. So we have this formula and a bound, corresponding bound. So f hat of xc decays like maybe I should put it less than or equal to some constant times 1 plus c to the minus n for some constant c. Just c, we'll just depend on the dimension. Okay, so this is smoothness of f implies decay of the Fourier transform. Right, so if f is a Cn function, then the Fourier transform decays like 1 over c to the n. And moreover, we have this nice formula. So this decay property will follow nicely from this formula. All right, so this is a little trickier. And why is it tricky? Because we're gonna want to do this by integration by parts. Integration by parts is something we know how to do for the Riemann integral, right? And in particular, we can justify it. When can we justify integration by parts? Well, if we have a nice like C1 function, and the support is compact, right? If we have compact support, if we have a C1 function is compactly supported, the Riemann-Lebesgue integrals agree with it, and we can use the integration by parts formula. So, so this formula will be easy to prove in the case of compact support. We're just going to integrate by parts. But to justify it for general f that are Cn, not necessarily compact supported, we're going to need an approximation lemma. So, so in particular, we're going to we'll need a preparatory lemma just so that we can approximate for the general case. So proof. So first, let's do a lemma, or maybe even before a lemma, I need maybe a definition. First, a lemma. So let phi be a C infinity function with the following properties such that phi of x is equal to 1 for every x less than or equal to 1. Maybe I want to use a different phi so that I can write it easier. Phi of x is equal to 0 if x in absolute value is bigger than or equal to 2. And always phi is between 0 and 1. So, and moreover, that's even. Say. And so what's phi look like? Here's the graph of phi. Here's 1, here's minus 1, here's 1, here's 2, here's minus 2. So it's a smooth function that's compactly supported and is equal to 1 on the interval minus 1 to 1. So even a lemma, is there exists such a phi? Okay. Look up. These are often called bump functions, I guess. Bump function. And then I'm going to let phi k of x to be phi of x over k for k and n. Okay, and then some properties. So if I take alpha derivatives of phi k, this is less than or equal to some constant depending on alpha possibly, times k to the alpha. Right, because every time I differentiate in x, I just get a 1 over k. A 1 over k comes out. Right, and just think of what's happening as I'm doing this for k getting big. I'm spreading this function out. I'm making it equal to 1 on the interval minus k to k, and then it has to decay to 0. By the time I get to 2k, so it decays to 0 like 1 over k. Okay, so this is these are the properties. So it's just saying that the slope of this function is like 1 over k. And note, for every alpha not equal to 0, the support of d alpha phi k is inside k less than or equal to x less than or equal to k plus 1. Sorry, 2k. Right, because the function only has is constant in here, and it only is non-zero derivative between 1 and 2, and once I spread that out, it becomes between k and 2k. Okay, so the lemma is as follows. So given such a phi, if f is a Cn function, just as in the statement of the proposition, d alpha of f is in L1, as in the proposition. Did I say this in the statement of the proposition? I think so. Yes. D alpha of f is in L1 with alpha less than or equal to n for every alpha less than or n. If we let fk to be equal to f times phi k for every k, then we have convergence in L1. Then the limit as k goes to infinity of d alpha fk minus d alpha f L1 is equal to 0 for every alpha less with length less than or equal to n. So just we can approximate an L1, even if we had, so this is clear, right? If alpha is equal to 0, not for the just for the function itself without taking derivatives, right? We're just clear we have a convergence in L1 as k goes to infinity. So the content is basically just that this still works after taking derivatives. So the proof show for so let's do alpha equals 1, and then we can kind of deduct from here. So clearly, phi k times, let's do alpha equals 1, d equals 1. So phi k times f prime minus f prime and L1 goes to 0 as k goes to infinity. Right, just take a function multiplied by a bump function, and then note the chain rule. And so hence it suffices to show that that phi k prime times f and L1 goes to 0. Right, by the previous two lines. Well, but in this case, and we have phi k prime times f and L1, this is less than or equal to a constant times divided by k times the L1 norm of f in the region x bigger than or equal to k, in fact. And this tends to 0 both because 1 over k tends to 0 and because so it really goes to 0. It goes to 0 for two, both because of this factor out in front. This is tending to 0 and this thing is tending to 0. So they're both tending to 0. So the whole thing tends to 0. Okay, so that proves the lemma. Now let's get back to the proposition. So we're trying to prove the differentiation formula for Fourier transform. So proof of the proposition. So if f again, let's do alpha equals 1, d equals 1. So if f is in C1 of R with compact support, can integrate by parts. F prime hat of C is equal to e to the minus 2 pi I x dot C, f prime of x dx and R, which is equal to, by integration by parts, I can just put the derivative over on this factor here. Right, and what do I get? Well, I get minus, I get 2 pi I C. I get integral, sorry, 2 pi I C of e to the minus 2 pi I x dot C f of x dx, which is just equal to 2 pi I C times f hat of C. Okay, and then now induct. For alpha greater than 1. Okay, so this handles the case when f has compact support. If not, if f does not have compact support, apply the above to phi k times f and let k go to infinity. So how does this work? So we'll look at the limit two ways. So on the one hand, by continuity and boundedness of the Fourier transform, and by lemma, d alpha fk, so let's let this be equal to fk, let's call this fk, d alpha fk tends to d alpha f hat uniformly as k goes to infinity. Right, to see this, this and L infinity, this is less than or equal to the L1 norm of this, which tends to 0 by the lemma. So this is the argument. Sorry. This is the argument to prove the statement above. Moreover, this goes to this. Fk hat goes to f hat uniformly because we have convergence in L1. Right, so convergence of the function in L1 means convergence in L infinity on the Fourier side. So L1 and L infinity are sort of dual with each other with respect to the Fourier transform. So this means 2 pi I C alpha times fk hat of C tends to 2 pi I C alpha f hat of C pointwise. And we're done. So see, right, because we can just complete the square here. So these two things are equal to each other. This tends to this tends to this. So by uniqueness of limits, these two, this is equal to this. So I have a nice diagram there. Okay, so the lastly we have the bound. So the bound, lastly the estimate, lastly the estimate so on the so to see this, so d alpha f hat of C is equal to 2 pi I C alpha f hat of C. This implies that C to the alpha times f hat is in L infinity, since d alpha of f is in L1. So d alpha of f is in L1 means this object's in L infinity, so this is in L infinity, and it's bounded by, in fact, the L1 norm of d alpha of f. So, and then lastly, we have this and 1 over there's some constant depending on d, 1 plus C, or maybe d and n. I think that's 1 over Cn. C to the n is less than or equal to some constant C to the n 1 plus C to the n. So here we can, so meaning in particular, this quantity times f hat is in L infinity, is bounded, which is the bound that we want to prove. And we're done. Okay, so we have these two. So first, maybe any questions? Okay. All right, so we have these two heuristics, right? If function is, sorry, let me just, I see that there's things in the chat. I want to make sure there's, can I sync the file? Okay, file, I'm just syncing the file again. So we have these two heuristics. One is the function is decaying, then the Fourier transform is smooth. And then conversely, if the function is smooth, then the Fourier transform is decaying. So it suggests that a nice space of a nice class of functions for which to consider the Fourier transform is the class of functions which are both smooth and decaying. Okay, so if you're both smooth and decaying, then we can expect the Fourier transform to be both smooth and decaying, right? Or decaying and smooth, and then vice versa. So we define what's called the Schwartz space. SCH. Note the spelling of Schwartz. So we'll call this script S is all functions f from Rd to the complex numbers such that a few properties hold. One, f is smooth, so it's in C infinity. Two, x to the alpha d beta f is a bounded function. For every multi-indices alpha beta. And that's it. Okay. So it's smooth and it's decaying. And not only is the function decaying, but all of its derivatives are decaying to any order, right? It has derivatives of all, or its derivatives to every order decay to every order. So you can just think of alpha being an arbitrarily large integer, and the length of alpha being an arbitrarily large integer, and the length of beta being like arbitrarily large integers. And those are all bounded functions. So this is a Schwartz class. And you can endow this with semi-norm or something. F alpha beta this isn't super useful in practice. This norm is this. So the alpha beta norm of f is just multiple. It's a weighted L infinity norm of the derivatives of f. Okay, and you have a notion of convergence here. So notion of convergence here, if you have a sequence of Schwartz class functions, converge in the Schwartz class to f in the Schwartz class if the limit as k goes to infinity of fk minus f alpha beta is equal to 0 for every alpha beta. So this is a restrictive class of functions, right? But it's a larger class of functions than the C infinity functions with compact support. So what are some examples of Schwartz functions? So examples. One, well, C infinity functions with compact support are Schwartz functions. Two, but what you should think about is enlarging the C infinity functions, those functions with exponential decay, and exponential decay of all their derivatives. So e to the minus, I like to put this here for normalization, so it's going to come up in a little bit, the Gaussian function, e to the minus pi x squared, norm x squared, is in the Schwartz class. So this functions and all of its derivatives decay basically because exponential decay beats any polynomial decay. And three, here's an example of a function that's not a Schwartz class function. So not in S are 1 plus x squared to the minus n. So this does not decay fast enough. So right, the polynomial decay is not enough to be a Schwartz class function. You must have super polynomial decay. You must decay faster than any polynomial. Polynomial rate. And then another example, this is not a Schwartz class function. So g of x is equal to e to the minus pi norm x squared. So I have Gaussian decay, but let's say multiply this by some oscillating factor, e to the, that's kind of crazy oscillations, e to the pi x squared. So g decays, but derivatives of g do not. So not only does the function have to decay fast, but its derivatives have to decay fast. So this function has decays crazy fast, but it has crazy fast oscillations too, which lead to its derivatives not decaying. Okay, so those are examples of not Schwartz class functions. Okay, so the Schwartz class is a nice space. So S, so properties. Maybe I won't really enumerate these. Schwartz class is closed under differentiation. Multiplication by polynomials. These are continuous operations. S, so i.e. sequential convergences is preserved. If fg are an S, then f times g is an S. So it's closed under multiplication. You can multiply two functions, you still get a Schwartz class function. So those are some nice properties. You can define the Schwartz class differently. So alternative definitions, maybe. Equivalent definitions. F is a Schwartz function if and only if 1 plus x to the n times d beta f bounded for every beta and n. If and only if the limit as x goes to infinity of x to the alpha d beta f of x is equal to 0 for every alpha beta. So if and only if this is decaying for every alpha beta. So there's a couple alternative definitions. If and only if f is in C infinity, and x the alpha d beta f L1 is bounded for every alpha beta. So these are three alternative characterizations, slight alternative characterizations. Okay. I'll capture the same class of functions. And proposition or lemma, compactly supported functions, C0 infinity is dense in S in the Schwartz class. For every f and s, there exists g and C0 infinity such that, or maybe like this, there exists fk, a sequence in C0 infinity such that fk goes to f and s. And the proof is not hard. Just take a Schwartz function f and set fk is equal to phi k times f, where phi k was the same phi k from earlier in the class. Okay. What else? Okay. So the point, or what makes this a nice class of functions, a very nice class of functions, a convenient class of functions to work with, is note that so smooth compactly supported functions are not preserved by the Fourier transform. If you take a Fourier transform of a smooth compactly supported function, you do not get a compactly supported function on the other side. The output is not compactly supported. However, if you take a Fourier transform of a Schwartz function, you get a Schwartz function as output. So the theorem is if f is a Schwartz function, then f hat is a Schwartz function. And then f, the mapping f to f hat, is continuous. on S. It's a continuous mapping on S. Okay, and then by the so later we're going to combine this with the inversion formula. To this is a but okay, for now, f is a Schwartz function and f hat is a Schwartz function. Let's see. I think maybe I have time to prove this real quick. It's not, the proof is not hard. So proof. If proof is not hard given what we've already done. So if f is a Schwartz function, then f is an L1, okay, good. Which means that, remember we're trying to see that f hat's a Schwartz function, so that we want to know that it's smooth, bounded, and all of its derivatives are smooth and bounded and decay faster than any polynomial. So what do we get right away? Just from being an L1, we get that f hat is bounded, right? Is bounded. Okay. So continuing like this, if f is an S, then d alpha x beta times f is bounded for any fixed alpha beta, since d alpha x beta f is a Schwartz function, right? So if f is a Schwartz function, then right, we can multiply it by a polynomial and still get a Schwartz function. Schwartz class is closure multiplication by polynomials. We can take derivatives of a Schwartz function, we still get a Schwartz function. So if you have a Schwartz function, just like I said in the beginning, if a Schwartz function, then its Fourier transform is bounded. So if this is a Schwartz function, which means that this thing is bounded, right? But then d alpha x beta. So here's a trick. D alpha x beta hat of xi is just equal to 2 pi I to the alpha minus 2 pi I to the minus beta times c to the alpha d beta f hat of xi. And we're done. Right, because what we're trying to show is that this is bounded for every alpha and beta, right? To show that f hat is a Schwartz function. Well, to do that, we just use the formulas that we just proved. So we're using both formulas that we proved for the for derivatives, multiplication, how Fourier transform mixes with derivatives and multiplication by x or by xi. Okay, so that was a little quick, but I promise you that everything that that's innocent quality here, we just did in the notes a few minutes ago. Any questions in the class? The next time we can prove that, we're ready to prove the inversion formula. And then next time, prove the inversion formula and Plancherel theorem. So when studying the Plancherel theorem, we're going to means we'll understand the Fourier transform on the Hilbert space L2, which is a natural setting for it. How to understand the Fourier transform of L2 functions, which is a little tricky because for the Fourier series, right, we saw that the L2 functions were contained in the L1 functions, right, on the line. Right, so sorry, if f was in L2, then it was in L1 as well. Sorry. Yeah, that's what I was going to say. That's not true for for functions on the line, right? That was true for functions in the circle, but not true for functions on the line. So we need to actually work a little bit to make sense of the Fourier transform of an L2 function, and we'll use the Schwartz class, and we'll have to define an extension of this operation to do. So this is a little bit trickier to do. Okay, and then I think so. The last class, then. So we'll have to just think about what to do, but I'll either discuss a little bit about PDE or the uncertainty principle, which is a big topic in harmonic analysis, and it's just another manifestation of the fact that you can't be simultaneous. Will be different. Uncertainty principle is a there's principle in I guess in the field. It's manifestations of the fact that you can't be localized. You can't have a function that's both localized, does localized Fourier transform, and function itself can't be both simultaneously localized. Okay, so we'll pick up next time with the inversion formula. Sync the file. Thanks, guys. See you later.
Thanks.
Thank you.
Thanks, Professor.
Bye-bye, guys.
I have one, like, not a content question because I know you have to go soon, but you said you're maybe going to be talking about some stuff with PDEs next week.
Maybe. I'll see how far I get. So yeah.
Because we have a problem on the uncertainty principle on the homework, which is a really fascinating problem. But I would love to see, like, if it matters at all, if you want any input. I think the PDE stuff would be really cool. But you do what's best for.
Okay, cool. Yeah, I won't get far with either thing. So unfortunately, yeah. So yeah, I probably will discuss a little PD. I can't do the class properly without ending with some PD. So
awesome, cool. Well, I'll see you later then. Thank you.
Bye, Tyler. Bye.
Bye.